Today we're going to talk about before and after gas laws. And here's your generic equation. You have P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. Any variables that are constant in a problem, you simply cross them out and that's your equation. So let's get started with Boyle's law. Boyle's law has PV equals K, where P equals pressure, V equals volume, K is a constant. What this says is that pressure and volume are indirectly proportional with each other, which means that when pressure increases, volume decreases. When pressure decreases, volume increases. Here's the law stated as a graph. And as you can see, as volume increases, pressure decreases. Boyle's law's equation is like this. P1 times V1 equals P2 times V2. The 1 stands for initial, the 2 stands for final. So Boyle's law only relates to pressure and volume, where temperature and moles are constant and they do not change. When you solve these types of problems, you need to make sure you define all variables. And before you even start putting in numbers for this equation, you need to make sure that your pressure units are the same. So go ahead and try this problem. A sample of helium gas has a pressure of 3.54 atmospheres in a container with a volume of 23.1 liters. The sample is transferred to a new container and the pressure is measured to be 1.87 atmospheres. What is the volume of the new container? So, when you figure out this problem, you get 43.7 liters. Try another example. A steel tank of argon has a pressure of 34.6 atmospheres. If all the argon is transferred to a new tank with a volume of 456 liters, the pressure is measured to be 2.94 atmospheres. What is the volume of the original container? Well, when you plug in those values, you get 38.7 liters. Charles' law. Charles' law looks like this, and it relates to obviously volume and temperature. So, how are they related? Well, when temperature of a gas increases, the volume will also increase when the amount of gas and pressure are held constant. This means volume and temperature are directly proportional. So, remember, any variables that are constant, cross out. So pressure and moles are held constant, so we cross those out. So there's our equation. V1 over T1 equals V2 over T2. 1, again, stands for initial. 2 stands for final. As you can see here, your volume needs to be in liters and your temperature needs to be in Kelvin. So make sure your temperature is in Kelvin before you even start. Here's a representation of Charles' law as a graph, and again, as you can see, there's a direct relation between temperature and volume. As one goes up, so does the other. So let's get some practice converting temperature into Kelvin. Remember this equation. Kelvin equals degrees Celsius plus 273. Okay? This is due to the fact that you can have a negative value for degrees Celsius, but we cannot have negative values when we're dealing with pressure or volume or moles. So therefore we have to have a positive scale, which is what the Kelvin scale does. So when you convert 16 degrees Celsius into Kelvin, you should get 289 Kelvin. When you convert negative 40 degrees Celsius into Kelvin, you should get 233 Kelvin. Here's an example problem using Charles' law. A 2.0 liter sample of air is collected at 298 Kelvin and then cooled to 278. The pressure is held constant at 1 atmosphere. What is the volume of air at 278 Kelvin? Your answer should be 1.87 liters. Here's another example. A sample of gas at 15 degrees Celsius has a volume of 2.58 liters. The temperature is then raised to 38 degrees Celsius. What is the new volume? Now, here's an example where you're given degrees Celsius, and you have to change it to Kelvin first before you can even begin. So when you convert those two temperatures into Kelvin, you should get 2.79 liters as your answer. Avogadro's law has to do with these variables. It has to do with volume and moles. Okay? So, as the volume increases, so does the number of moles, which is why they're directly related. Okay? When you keep the temperature and the pressure constant. So again, here's your equation. V1 over N1 equals V2 over N2. 1 again stands for initial, 2 stands for final. Okay? So we get that equation by simply crossing out the constant values. In this case, temperature and pressure are held constant, so there's our equation. As a graph, again, as volume increases, so does the number of moles, and vice versa. Here's an example problem. We have 2.55 moles of helium gas occupying a volume of 59.5 liters at a particular temperature and pressure. So what does the volume of 7.83 moles of helium occupy under the same conditions? Well, you don't have to convert anything here. All you have to do is plug them into the equation, and when you do that, you get 183 liters. Lusak's law. Lusak's law relates to pressure and temperature, and pressure and temperature are directly related when the number of moles and volume are held constant. So in other words, as pressure builds, temperature also increases. Lusak's equation is this, where you have P1 over T1 equals P2 over T2, 1s and 2s, initial and final. Pressure can be in any unit as long as you're consistent with P1 and P2. Temperature has to be in Kelvin. Okay? Here's our equation again, and we're going to cross out moles and volume, and there's our P1 over T1 equals P2 over T2. As a graph, as temperature increases, so does pressure. Here's an example problem. Suppose you use an aerosol can that contains a gas at 760 torr and at 25 degrees Celsius. This can is heated in a fire to 500 degrees Celsius, then what will the final pressure of the gas inside the can be? Well, in this case, you see degrees Celsius. You have to convert to Kelvin first. Then you plug in your equation, and you should get 1,971 torr as your answer. The combined gas law is when the number of moles is held constant. So there's our equation. P1 V1 over T1 equals P2 V2 over T2. Remember that in the combined gas law, your moles are held constant and your temperature must be in Kelvin in order to convert. Here's an example problem where I'm giving these variables and I'm looking for the second volume. Notice how my pressure changes. Notice how my temperature decreases. I'm in degrees Celsius for T1. I got to change it to Kelvin. Okay, everything else is okay. When I plug it into the equation, I get that when I rearrange the variables and solve for V2. And I should get 124 liters as my answer.